Okay, so today I'm going to start talking about singular holomorphic foliations. And to start with, let me consider X a holomorphic vector field that is defined on an open set of Cn. And a first attempt to try to define a singular holomorphic foliation, I can do the following. So take x of x as being the singular set of the vector field x, and on the open set U minus this singular set, we have a regular vector field defined on N, so that it defines a regular foliation. Okay? However, if we think on this vector field x as being written as f1 dd x1 plus tilde fn dd xn, and if you assume, for example, that the singular set of this vector field has codimension 1, then we have that these functions f1 tilde f tilde of n have a common factor. Okay, so if you take not x, but if we take a vector field y that is obtained by x dividing by all common factors, what happens is that the vector field y defines exactly the same foliation, the same regular foliation, away from the singular set of x. Okay? So y defines the same foliation, or the same regular foliation as x away from the singular set of x. And in that case, we have also that the singular set of the vector field y is such that its codimension is at least 2. Okay, so having a vector field, the vector field defining a foliation on some regular part is not unique, okay? But because of this remark, we can always assume that it is being defined by a vector field having codimension, singular set of codimension at least 2. Okay? So the formal definition. So a singular holomorphic foliation on a complex manifold M okay, consists of the following data. we have an atlas UI phi that is compatible with the complex structure of the manifold M. And the homomorphisms phi, they are going from UI to some open set Vi on Cn. Okay. We have vector fields x, y defined on this Vi, and by the remark made before, we can assume then that the codimension of the singular set of these vector fields is at least 2. And whenever we have two open sets having non-empty intersection, so if UI intersecting with J is non-empty, then there exists a function Hij going from the image by phi of this intersection on C, such that the push forward of phi j composed with phi minus 1 of the vector field x, y is Hij times the vector field xj. Okay, so essentially, I'm going to make a picture here. So we have the manifold M. We have here two open sets, Y with J. We have these homomorphisms, A phi I and phi j. Okay, sending our vector fields here. We have our vector field here defined. Okay, and I can take phi j composed with phi I minus 1. So I'm sending this vector field not exactly to the vector field that is defined here, but to a multiple of this vector field. Okay, so they don't have to coincide, but it is a multiple of them. At least the directions coincide, so they define a foliation. Okay, if these H, I, J are all constant equal to 1, then we have an actual vector field on the manifold M. Okay, so I will focus essentially on one-dimensional foliations, holomorphic foliations, and also in codimension 1 singular holomorphic foliations. So let me write the definition for the codimension 1 foliations. So a singular so here I forgot to put one-dimensional. So a singular holomorphic foliation on M of codimension 1 consists now of the following. Again, we must have an atlas that is compatible with the complex structure of M. Again, these phi i's are defined from Ui into an open subset of Cn, as before. Now, instead of holomorphic vector fields, I would have, here I forgot, holomorphic vector fields. I must have holomorphic one-forms. Wi defined on Vi. We can assume as well that the codimension of the singular set of these one-forms is at least 2, since the same remark works for this case. But now I have to join here the integrable condition. Okay, so Wi dWi must be equal to 0, so that the distribution defined by the kernel of Guy is integrable. Okay, and again, we have that if we take 2 of these open sets having non-empty intersection, there exists, okay, again, a holomorphic function hij such that the push forward of phi composed with phi j minus 1 of the on-form Wi is this function times Wj. Okay, so as I mentioned yesterday, when we are on a manifold of dimension 2, one-dimensional foliations coincides with codimension 1 foliations, so we can always think on vector fields or on one-forms defining our singular foliations. Okay? So let me give examples. So the first example is a foliation on the complex torus. Okay, so let me start by considering a lattice on Cn. And let me take the torus defined as the quotient of Cn by this lattice. Okay, and on Cn, I can consider Y a non-zero constant vector field and this non-zero constant vector field, it is invariant by the translations associated to this lattice. Okay, so in fact, it induces a foliation on the torus. Okay, so it descends to a holomorphic vector field on the torus, defining a foliation on the torus, that in fact this is, in this case, a regular foliation. Okay, so in this case we don't have singular points. And the second example that I'm going to give is more important, and it corresponds to foliations on the complex projective space. Okay? In fact, I'm going to present it on the complex projective plane, but there is an obviously generalization for the complex projective space. Okay? So there are two different ways to construct foliations on the complex projective plane. Okay, I'm going to present these two ways of constructing the foliation, and in fact these constructions are totally equivalent. Okay, so there are two different ways, so different but equivalent ways of constructing singular holomorphic foliations on CP2. So I'm going to do it on the projective plane. Okay, so the first construction, I can think on the following. So I'm going to look to CP2 has the equivalent classes of C3 minus the origin quotient by the relation where 2 points Z and Z prime are equivalent if and only if they are collinear. Okay? So there must exist a lambda on C star such that Z is lambda Z prime. Okay, so thinking on that way, let me consider X as being a holomorphic homogeneous polynomial vector field on C3, okay? And I will write X as P xyz ddx plus Q xyz ddy plus R ddz, okay? And let me consider the action of C star on C3 minus the origin, defined as I take a lambda on C star, and I will associate the map from C3 minus the origin to itself, such that to each point x, y, z, I associate lambda x, lambda y, lambda z. So, if I consider x composed with sigma, so x on sigma xy z, I can easily check, because X is homogeneous, that this coincides with lambda d time x, where d corresponds to degree of the vector field X. Also, if I calculate the derivative of x, of sigma applied to x, so the derivative is simply lambda times the identity, so this is lambda x. Okay, so it then follows that this sigma on x coincides, so this sigma on x coincides with lambda d minus 1 times x. Okay, so what happens if I take the pullback of x by sigma? This does not coincide with x, but this is a constant multiple of x. Which means that, in fact, the directions of the vector field X are preserved by the action of sigma, or I mean, it is preserved by homotheties. So the directions of X are preserved by homotheties. Sorry?
You've just written d sigma x is equal to lambda x, and you get d sigma x is equal to lambda.
Sorry, the pullback.
Yeah.
Thanks. Okay, so since it is preserved by the homotheties, it then follows that the vector field X defines a singular holomorphic foliations on CP2. This is true unless the vector field X coincides with a multiple of the radial vector field. So if it is a multiple of x ddx plus y ddy plus z ddz. Okay, because in this case, the integral curves of the differential equation associated to this vector field is exactly the straight lines passing through the origin. Okay, so it induces just a point in CP2. Okay? Okay. One of the things that I can see in this construction as well is that if H, in fact, does not coincide with a multiple of the radial vector fields, then the singular set of the foliation they are in correspondence with the straight lines passing through the origin that are invariant by the vector field X. Okay? So singularities of the foliation on CP2, okay, so are in correspondence with the straight lines passing through the origin and that are invariant by X. Okay. Okay, so the second way to construct the foliation is essentially by thinking that CP2 can be viewed as a compactification of C2 by a junction of the plane at infinity. Okay? So I will say that CP2 is C2, and I will denote the plane at infinity by delta infinity. Okay? And now, if I have X, a polynomial vector field on C2, so if X is Pxy ddx plus Qxy ddy, I can say that X has a meromorphic extension to CP2. Okay, so for example, I can equip CP2 with the following affine coordinates. So I have x, y, the coordinates on the initial C2. Then I can consider coordinates u, v, and zw, where xy corresponds to 1 over u, v over u, or xy corresponds to 1 over w, z over w. Okay, so I will make the calculations in UV. So in coordinates UV, the vector field X can be written as follows, or the extension of it. So it is the vector field, if I denote it by HV. This is the H minus 1 composed times X composed with H. Okay, so this is minus U square 0 minus UV U applied to P1 over UV over U, Q at the same point. And taking this product, we get that this is U minus U P at this point, ddu, plus minus V P at this point, plus Q at the same point. And if I denote by K the order of X, so the minimum order between P and Q, I can write this vector field Y as 1 over U K minus 1 times U times a vector polynomial on U and V, plus minus V, the same polynomial P tilde on that, more a polynomial also in U and V. So since when you are trying to define a foliation, it doesn't matter the common factors that we have here in front, I can simply forget this part and say that the foliation is induced by a polynomial vector field. So it is, in fact, a holomorphic foliation nearby the v equal to 0. And we can repeat exactly the same calculations to the coordinates zw and check that, in fact, it is a holomorphic foliation on all of CP2. OK? So repeating the calculations on coordinates zw, we check that X induces a holomorphic foliation on CP2. Okay, so these are two ways of constructing the foliation, and both constructions, they are equivalent in the sense that they produce exactly the same foliations. Okay, so those constructions are equivalent in the sense that they produce the same foliations. But more than that, every foliation on CP2, every holomorphic foliation on CP2 can be constructed in this way. Okay? So these constructions give rise to all holomorphic or singular holomorphic foliations on CP2. Okay. So next, I'm going to talk about the holonomy. That is one of the tools to study foliations. And I'm going to start by looking for the holonomy of a leaf of a foliation. Okay? So let's have be a foliation or be a holomorphic foliation on a complex manifold M. Okay? I can assume that it is singular. If I don't mention now, it's that I'm assuming that it is singular. Otherwise, if I assume that it is regular, I will write explicitly that I'm assuming it to be regular. Okay? So let L be a leaf of this foliation. Okay? And now, for example, I'm going to draw a picture here. I will assume that I'm with one-dimensional holomorphic foliations. So I have here my leaf. the leaf has complex dimension 1, but it has real dimension 2, so that I can consider paths here on the leaves. Okay? So I'm going to consider here a path on the leaf, such that the initial point is a certain point P0, the final point is a certain point P1, and maybe I'm going to draw there because I have to draw something else, and this will be very small. So I'm going to continue with my picture here. And I'm going to make path transverse sections to this leaf. Through each one of these points, P0 and P1 respectively. Okay, so I have a transverse section here, sigma 0, transverse section here, sigma 1. Okay, and what we have is that there exists a partition of the interval 0, 1. So we have 0 is T0, less than T1, less than T2, and so on. Such that when we look to the image by the path of each interval Ti plus 1, this is totally contained in one of our open sets of the cover of M. Okay, so I have here my partition. Okay, two consecutive elements are in a same open set. Okay, and taking alpha, for the notation, I'm denoting by Pi over K as the image of Ti. Okay, and I will consider sigma I over K to be a transverse section to L through this point Pi over K. Okay, so through each one of these points, I will also consider here transverse sections. Okay, so for example, if I look to this open set here, UE, I have here my map Pi, okay, and the foliation here corresponds to horizontal lines if you are on one-dimensional foliations, or horizontal planes or hyperplanes. Okay. Obviously, this intersects here. I can look what happens to the consecutive open sets. But here, what I have is that these transverse sections here, they are also transverse sections here. Okay? So this point here will correspond to this point. This point here corresponds to this point. Okay? They are in the same leaf. And now, as far as I consider a point here on this transverse section, it corresponds to a point somewhere here on this straight line in blue. Okay, and I may consider the lift of this line, and the leaf or the plaque, since we are in an open set, passing through this point will intersect this transverse section in a unique point. Okay, so for every x that we fix on one of these transverse sections, okay, and being x sufficiently close to this point P A over K, okay, then the plaque through x intersects sigma I plus 1 over k in a unique point. And this unique point we will denote by fi of x. Okay, so in my picture above, it will intersect here somewhere. Okay, I have to assume that x is sufficiently close to the origin. Okay, we don't know what about singularities outside. Yeah.
When you say section, you mean section or section? You don't mean say transverse section.
So you have a manifold, and you can take a transverse manifold to this initial manifold. So I call it a transverse section. Okay? And it is only defined locally. I'm not considering, for instance, a global one. Okay? Okay. So one of the things that I can say at the domain of definition of Fy need not to be this transverse section, okay? But it contains a disk around this point here, okay? So contains the domain of definition of Fi contains a disk di over k. Okay, so I want to glue all this picture. So what I'm going to say is, okay, I start with P0. I look to this transverse section here, and I look to points nearby this point here. Okay, I can do this thing to these open sets. I arrive to another point here. Maybe I arrive to some points where the next map is not well defined. Okay, so I may reduce a little bit the disk I start with, okay, and I will continue passing to the next section, and so on and so on. Okay, so I will consider the map where I first apply F0, then I apply F1, and so on and so on, and lastly I will apply Fk minus 1. I will denote this map for F gamma, okay, And I know that f gamma is well defined in a small neighborhood of the origin. Or if I prefer, in a small neighborhood P0 on the transverse section. Okay, and up to reducing this section, I can assume that it is a disk. Okay, so the map f gamma that for Abusov notation, I will say that goes from sigma 0 to sigma 1. In fact, it can be found in a smaller subset of sigma 0, and I can assume that sigma 0 is already this smaller subset. This is called the holonomy map associated, the holonomy map of L associated to gamma. Okay, so I'm putting here up to rescaling sigma 0 just to be sure that everything is well defined on it. Okay, so to say that this is the holonomy map associated to gamma, I have just to make some remarks. So the first remark is that this holonomy map does not depend on the partition that we have considered in the interval 0, 1. Okay, it does not depend also on the open sets Ui in the cover of M that you consider. Maybe you can make another choice, and this does not depend on this choice as well. And it does not depend on the transverse sections. Transverse sections. Sigma I over K that you consider. Okay? So this is well defined. Second remark is that f gamma is a diffeomorphism. Okay? In fact, this f gamma admits an inverse. That corresponds to f of gamma minus 1. So instead of going from P0 to P1, I assume that I'm going to P1, from P1 to P0. Okay, so this gamma minus 1 is simply defined as gamma at 1 minus t. Okay, and finally, the last remark is that if the foliation is holomorphic, then this map f gamma is holomorphic as well. Okay, so what happens if you consider a different path joining P0 to P1? Okay, again, let F be a foliation. Again, let L be a leaf of this foliation, but now I'm going to consider two paths, gamma 0 and gamma 1. Such that the initial point coincides as also the final points. Okay. We consider again sigma 1 and sigma 0 and sigma 1 to be transverse sections to L.
Well, you can say that, I mean, it seems that the dependence is topological in this path. Why you can say that the map is holomorphic?
No, because, for example, we are assuming the foliations to be holomorphic. Every map that you are assuming, in particular when you are passing from UI to J and so on, everything will be holomorphic.
But the fact is only continuous. This does not mean, this does not...
For example, if you consider one-dimensional foliation, imagine, okay? So you are assuming that you have a holomorphic vector field defining it. Take the flow box theorem, for example. You have the ddx1, so everything will be holomorphic. Okay, and then if you are trying to glue different open sets, the glue is holomorphic as well. So, okay. Okay, so gamma 1 and sigma 1 and sigma 2 are also transverse sections to L at P0 and at P1 respectively. And what we should consider now is not the maps F gamma 1 and F gamma 2. We should consider phi gamma 0 and phi gamma 1 as being the germs of F of gamma 1 and F of gamma 2 at the point 0. Okay. Then, if gamma 0 is homotopic to gamma 1, then the germs of these maps coincide. So I cannot say that both of them coincide. They can have eventually different domains of the definition, but their germs coincide. Okay?
Gamma 0 in 1?
Gamma 0 in 1, thanks, and gamma 1 in 1, thanks. Sorry? I cannot lose.
When you define a homotopy, you need to restrict in which area it homotopy to gamma. So you have a...
You can make a deformation from one to the other.
Yeah, so but it's deformation inside A or outside A?
Inside the leaf. Okay? Okay, so a particular attention is given to the case where the paths gamma are in fact loops. Okay? And in this particular case, for simplicity, we will assume that the two transverse sections sigma 0 and sigma 1 coincide. Okay? And thus, in this case, phi of gamma, okay, so the germ is a germ, is an element of the group of germs of the diffeomorphisms of sigma 0, preserving or leaving the point P0 fixed. Okay, so if we let gamma vary, what you get is a homomorphism phi from the fundamental group of the leaf L at P0 into this group that I will denote by diff of sigma 0 P0. Okay, and to every class of gamma that I consider here, I will associate the germ of f at gamma. Okay, and for us, the image of this map is called the holonomy of the leaf at P0. Okay, so what happens if we vary the point in the leaf? Okay, so let us now assume that I have another point in the leaf passing through this point P0. Okay. Let me consider sigma to be a path joining P0 to the point P1. Okay, and that's what I can say is that sigma induces an isomorphism between the two holonomy groups. At the two holonomy groups. Okay, so let me denote here this group by holonomy of L P0, and I have here that this induces an isomorphism L from the holonomy of L at P0 to the holonomy of L at P1. So how can we see this? It suffices to make a picture. So I have here my leaf L, my point P0, my point P1, and I have here the path sigma joining one point to the other. I take here two transverse sections to each one of these points. Okay, and now what I should do is I start in this point. Okay. If I consider a point here, I will take the lift above sigma minus 1 of this point. Then I take a loop mu here. So I look to the image through that. Okay, I take the lift, and then I will return by sigma to P1 again. Okay, so this is the construction. So sigma star of phi of mu is simply the composition of these elements. Okay, so the only thing that I have planned, but I'm in time, to make before passing to the holonomy of affiliation transverse that are transverse to a fibration, it was just to give an example. But I can make it tomorrow if it...
So these two subgroups conjugate inside
Yeah.
the sigma 0 pizia.
Well, in any case, I can give the example tomorrow. I'm in time. I don't know.